Alright, this lecture is on metamorphic rocks and processes. We're going to be able to access, if you want to go back and look at this slideshow, you can actually view rock samples that I talk you through in class. Alright, moving on. The rocks in the Earth's crust, you can see that they're dominated by igneous rocks. About 65%, almost 2/3 of all rocks on Earth in the Earth's crust are igneous. And about 2/3 of those are basalt. So basalt by far and away is the most common igneous rock, most common rock on Earth's surface. And the second grouping is metamorphic, where gneiss dominates that category, about 78%. And then there's sedimentary. These are kind of the cover from sedimentary processes, and that's about 8%. And shale and other mud rocks dominate sedimentary rocks and sedimentary rocks that we find in the Earth's crust. So all total, these are the rocks in the Earth's crust by percent. Here we can see a better breakdown, and you have this picture in your binder. Just make sure you've been able to take a look at it. Just shale and siltstones, just mudstones. Then we've got sandstones in the mix and a little bit of limestone and other sedimentary rocks. So that's sedimentary. For metamorphic, we've got gneiss and then schist, and then marble and other metamorphic rocks are just a small percentage. And then lastly, basalt and mafic minerals dominate, and then there's granite and other kind of felsic intermediate igneous rocks. So we move on in the rock cycle, and we started off studying igneous rocks, and we studied sedimentary rocks, and now we've moved on to metamorphic. Metamorphic rocks are formed at variable depths within the crust when pre-existing rocks, including igneous, sedimentary, and other metamorphic rocks, are changed physically and chemically due to the change of the temperature, pressure, or both. During metamorphism, the texture or mineral compositions, or even both, of pre-existing rocks change under various metamorphic conditions at different depths. We can see this when we look at a map of the Earth, that we can say that, okay, we've got these Precambrian, these really old igneous rocks here that are found on the Earth's surface. We find these are the kind of the oldest rocks. These are kind of the base of continents, right? We find them all over on every continent. But we find folded mountain belts. This is where we find metamorphic processes, where you get extremely high temperatures and pressures. And that's what we see in green. So the Appalachian, the Rockies, kind of the western part of South America, and all over. They're really scattered. And then we have younger sedimentary rocks that kind of cover them. And that's sedimentary rocks are generally from when oceans kind of, when they rise and fall. Foliated metamorphic rocks are common where we find mountain building processes, including shields and mountain belts. High temperatures and pressures lead to changes in rock while in the solid state, and that's very key. They're still solid. They don't melt. If they melt, what defines it as igneous. So here we can look at temperature, pressure, and chemically active fluids change pre-existing rock into something new. And we talk in terms of foliation. This is a textural issue. High foliated, we would say gneiss. Gneiss, we actually call this banding. Banding tells me that it's extremely highly foliated with alternating light and dark minerals. We could say that the dark minerals are predominantly biotite and or hornblende, and the light minerals are quartz and feldspar, your plagioclase. And then we move into kind of a slightly lower grade of metamorphism, and we see that it's got less foliation. This is actually a schist, and schist we would say has schistosity. And the schist we have in class include garnet schist and muscovite or mica schist. Moving on, lower grade is phyllite, and I want you to pay attention to the locations of where these are. This is deep in the kind of the base of a mountain. High temperature, high pressure. We get less temperature, less pressure. Lower yet, and even lower yet when we get to slate. In slaty rocks, we would call, well, slate itself, we would say has a slaty kind of texture. And phyllite has kind of slaty at times. But it's not quite in the schistosity region. So we've got these specific terms, and we'll get to those here very shortly. Next one. I want to just give you an example. So where I find subduction, this is kind of the holy grail of geology, that we have these extremely high temperatures and pressures taking place. This would be an area of high temperature, high pressure. You can see this right here. And this has a very specific kind of a mineral-associated facies. And I don't necessarily want you to look at anything more, but just realize that plate boundaries are where all kinds of geologic activities are taking place. Here we find a subducting plate at a convergent boundary. We find volcanism, partial melting, and metamorphism of rocks. That this region illustrates a wide range of temperatures and pressures. Here, this zone right here, low temperature, it's near the surface, but very high pressure. This is where your plates are colliding together. Up here we'd say high temperature, right? We have liquid rock that's heating, but low pressure. It's not under the weight of the rock above it. So that's just an example for you to look at. In this slide, we'll see this low grade. This would be the parent rock of slate. And generally we'd call this shale, but since it's within a metamorphic range, I would say this would be kind of an in-betweener between slate and shale itself, the parent rock for this. But once we start having metamorphosis take place, we get this very nice sequence, and we would say slate into schist, and phyllite is missing here, but we could just jump right from slate to schist into gneiss. And gneiss, we get these very defined bands. That these are higher grade metamorphic rocks. They've just been metamorphosed. They've been subjected to more temperature and pressure. And we can see that again here. And these are the rocks we'll need to know. We've got slate that comes from muds, right? Shales and mudstones. They have good cleavage and they have dull, smooth surfaces. Whereas phyllite is also fine grained, but its parent rock is slate. So really you take slate and you continue to heat and add pressure to it, and it becomes phyllite. It breaks along wavy surfaces and it has a very glossy sheen. I would say get used to seeing phyllite in terms of its glossy sheen. That's kind of the primary identifier. In schist, the parent rock to schist is phyllite. That phyllite under greater temperature and pressures, it then starts to take on these characteristics. That minerals tend to grow along these particular, let's just say they elongate perpendicular to differential stress. And we'll get into that here in just a moment. But here I have schist, phyllite is the parent rock, and by the time I get to gneiss, I've taken either schist or granite or another igneous rock, but generally schist and granite are the parent rocks. If I continue to compress them and add temperature, heat, they become medium to coarse grained, that I can see the crystals themselves in here. And these are my foliated textures. My non-foliated textures, right? We've looked at texture this whole year on different rocks. Marble has medium to coarse grains, and its parent rock is dolostone or limestone. And we could identify that by dropping HCl. And these have interlocking calcite or dolomite grains. If it effervesces vigorously, its parent rock was limestone, it's made up of calcite. If it effervesces mildly, its parent rock was dolostone, and it's composed of dolomite crystals. Here we have medium to coarse, we could say quartzite. It is made from the parent rock of quartz sandstone. These are fused quartz grains and very hard. It has a hardness of 7 on Mohs hardness scale. And lastly, we have anthracite. Anthracite is essentially metamorphosed bituminous coal. It has a very shiny black, almost a light color, a light weightness to it. I didn't mean light, I meant kind of a light weight to it. But these are my 3 non-foliated, and when I look at textures, determine if it's foliated or non-foliated. So when I go back and look at pressure, when I talk about direct pressure, we're talking about stress. That under directed pressure, called stress, newly formed sheeted and elongated minerals such as mica and hornblende tend to grow along the direction perpendicular to the compressional forces. So if I have this would be before metamorphism. I might have a granite here, I might have even a schist. When I continue to add pressure to it, the minerals align themselves. The resulting parallel linear alignment of sheeted or elongated minerals is defined as foliation. So here would be a granite, and here would be the gneiss with the alternating light and dark bands of minerals. We see the light ones, they align themselves to the least amount of stress. And we can see that again here. Stress changes everything. Before metamorphism, they're kind of randomly distributed. After stress, they elongate. They align themselves very simply in their preferred orientation. So during the deformation where stress is not uniform or uniformly oriented, metamorphic rocks develop textures in which the mineral grains have strongly preferred orientations in the direction of least stress. And the resulting mineral alignment gives the rock a layered or banded, and I want to focus on the word banding, texture called foliation, and that's Latin for splitting into leaf-like layers. Here I can look at the degree of metamorphism, and we call these index minerals. And if I drew a line straight down this 300, I'd say that these are the minerals associated with the low-grade metamorphic rocks. I could call 500 kind of the intermediate, and if I drew a line down here, you would see that if it has these minerals, it tells me that they formed at these temperatures. And if they were high temperatures, like 7 to even 800 here, I could draw a line here, and I could say that if it has these mineral combinations, that it formed under those temperatures. And we're looking at temperature as our x-axis up here, and the minerals are our y-axis here. So low temperature, we'd say chlorite, epidote, and muscovite. These appear very commonly in low-grade metamorphic rocks. I could say biotite, hornblende, starlite, even garnet, these can form an intermediate. And high temperature, really if you find pyroxene with anything else, we would say those are high grade metamorphic rocks. So here are the samples we have in class. Highly foliated, we call this banding, right? Gneiss has this banding characteristic, whereas the schists, we would define those as schistosity, and these are the high-grade, coarse-grained metamorphic rocks. And then we get to phyllite. This actually has kind of a slaty cleavage like that of slate itself. So here's what we're looking at. Rocks can become other rocks. The protolith is the parent rock that can be sedimentary, igneous, or metamorphic. But we could take shale with these randomly distributed mud grains, and we can compress it. We can add pressure to it, and it can become slate. And notice the minerals in here begin to align themselves perpendicular to stress. And if I continue to add heat and pressure, that becomes schist, and then eventually they become very noticeably banded, and these would be your mafic, your biotite, and your hornblende, and the light would be your quartz and your feldspar. My non-foliated metamorphic include marble. These effervesce in the presence of weak acid. Due to calcite, it would be vigorous effervescence. Quartzite has interlocking grains. Quartz has a hardness of 7. And we have anthracite coal, the highest grade of coal. It's generally clean coal. It's metamorphosed from bituminous, the next lower down grade of coal. So non-foliated metamorphic rocks. If I looked at sandstone under a microscope, I'd see sand grains with these spaces of cementing material. And because quartz can be dissolved over time, we would say silica is likely the cementing agent. But under the microscope quartzite, these crystals are intergrown. These are all quartz crystals that are intergrown. Whereas limestone, these are shell fragments. We would say that calcite, right? Calcite is the mineral that makes them up. It's going to dissolve and cement them together. This would be your cementing material. Whereas marble, which is intergrown calcite crystals, essentially limestone metamorphosed, we'd see those calcite crystals intergrown. That viewing these under the microscope tells a much deeper mineralogic storyline. And here we see exactly how the parent sample compares to the metamorphic sample. And here's a picture of sandstone to quartzite. That quartz sandstone squeezed into quartzite. Individual sand grains cemented together are fused under the increased temperature and pressure into the quartzite we see here, interlocking. And this last slide we'll look at is called impact metamorphism in shocked quartz. And this is a picture from Barrington craters in Flagstaff. It's often called Meteor crater. And what we have here is the shocked quartz is the result of a high energy impact, also found at nuclear test sites. It's very rare to find shocked quartz, but when you find it, you know that it's the signature of a very, very high temperature, high pressure impact. And we would say an impact would be kind of an asteroid or a comet or a fragment of rock that blasted the Earth's surface enough to create these sets of intersecting, what we'd call them shock lamella, and that's what this term is here. That the quartz grains, if I magnify this, I get this very distinctive, let's just say they're called lamella, but they're these lines that we see in here that are signatures of very, very high temperature pressure scenario, and that's from an impact of something in space that collided with Earth. And we'll find in geologic time, those are not very uncommon. They're actually quite common.